Hi everyone, good afternoon. I'm Rob Knight, I'm a technical strategist for SUSE. It's my job to help support our guys in the field for all of our new application delivery products, as well as SUSE Manager.
Good afternoon, my name's Steve Hogg, part of the technical strategist team as well. My focus is more on the public cloud side.
Thank you. So today we're going to talk a little bit about microservices architecture and kind of give a very brief introduction to them. Going to kind of briefly explain why some of these things are important, and then we're basically going to talk through the 12 factors. Now, today, if you've been in any of the similar sessions like this, you may have heard the phrase 12 factors so many times, but not actually, come across them before. So we're going to kind of literally just walk through each of the 12 factors. These are the kind of common microservice, design patterns that people talk about. And then, Stephen's going to kind of talk us through a little bit about how the public cloud can help us with some of this. Okay, so talking about the kind of the world of a digital transformation company, one of the key messages which we want every company to kind of leave with today is that every company is now a tech company. Applications are key to every company around the globe. Therefore, whether that company consumes applications from an external vendor, or they make them themselves. In essence, that company is a tech company. A lot of the changing trends in IT are driving new business opportunities, and the requirements for these are very much changing the way in which we kind of look at applications, and the way that we focus on these things. In the past we focused a lot more on stability. Now it's kind of shifted to agility, getting your code and your updates to your code or your product out there faster. Because these application requirements are changing, so are the ways in which the applications themselves are designed, built, and ultimately delivered as well. This really is kind of across all industries. For instance, we've got like 3D printing that's impacting housing. You go and get the ability to have parts of a house pre-built 3D printed now. And big data and data analytics can impact or help any organisation kind of achieve their needs. So this is ultimately, why almost every company now is at heart a technology company. In terms of application delivery now, and why we talk about application delivery, and why is there a push for application delivery? Ultimately, the final aim of it all is to increase business agility and speed up innovation for an organisation. But there can often be kind of confusion. What does accelerate application delivery actually mean? Fundamentally, we're talking about reducing cycle times to getting code out there faster. Perhaps moving towards continuous integration or continuous delivery. Increasing the frequency at which code is pushed out, whether that's for consumption internally within an organisation or to your customers. And the faster that we can get that code out there, the quicker that your developers can get feedback on that code, and then ultimately that will result in a much better product overall. Another kind of aspect to this as well is building applications that can thrive in the cloud, and whether that is a public or a private cloud. The way that we think about apps in the cloud is a little differently. We need our apps in the cloud to be highly available, dynamically scalable based upon response to demand, but also evolve at a much more rapid pace as well. So kind of taking a look at how enterprises are doing these today, there's a lot of different technologies kind of at play here. We talk often about containerizing applications, doing that to help increase the dev test cycle. Containers can help us move to production a lot quicker with applications, and there's some kind of sessions dedicated to doing just that. But also by utilizing technologies like containers, we're freeing up the operations team from having to worry about managing all of the application suite within an organization, and worry more about the platforms that those applications run on, and then the developers will worry about the applications on top. And this is kind of all about standardizing the overall kind of software development process. It's about kind of turning software development into almost like a factory, within an organization. Code coming in, and then the artifacts of that code, the containers coming out, which can then be run and deployed. And this is kind of where microservices have kind of come into play. Now, this is a diagram taken from the Nginx website, and it's an example of how perhaps an application was architected a few years ago. Some may say that this is the legacy way, but there are still applications being designed this way today. One kind of big central blob that does everything. The example here is a taxi application, say something like Uber. All of the different functions within that application are kind of a part of the core of the application, and then on the outside we've got adapters that interface with external data sources. But there's a lot of limitations with an architecture like this. Say, for example, if I were to have a look over at payments, with this being one single application, when Apple and Google Pay launched, if I wanted to incorporate Apple Pay and Google Pay support, I would have had to code that in and then release my entire application, update my single application that I have for my taxi service in one go. Now just kind of bear that in mind, because as we start talking about microservices, that picture changes. So microservices, we start breaking things down into their individual component pieces, and we'll see there that there is a dedicated kind of cube that we've got for payments there on the right-hand side in the middle. Now what that means is that I can update the payment part of my application without impacting the availability of any of the other services. Adding Apple and Google Pay support is just a matter of those developers updating the payment service. All of the other services, they may interface with the payment service, and they do that through APIs, but the overall application, the whole suite, doesn't have to be taken down and updated. Because when we did things like this, quite often this would mean scheduled downtime out of hours, and then we'd copy over our big application binary or install the RPM, and then launch and then run some integration tests. This can be run on the individual service that it impacts. In addition to this, there's other benefits. So if I were to have a look again at the payment service, I need developers perhaps that have experience in payment systems or payment processing systems. That means that for my team, my specific functional team that deals with that individual payment service, they don't need to worry about anything else in the platform. Because they code the payment service and they publish what it can do via an API, everyone else just kind of consumes that. It means that their skills aren't wasted. It also means that we don't need. What I'm trying to say is that the teams are more specialised at the functions that they're actually working on, and that results in overall a development team overall that's much more capable at delivering for the different specialities that they need to. Whereas if we didn't have that, kind of everyone would have to be kind of good at everything, and you'd end up with jacks of all trades, kind of master of none type of situation. And this kind of is where the 12 factors come in. Now, a 12-factor app, it's a kind of a concept. It's 12factor.net, and it was originally published for the Heroku app publishing kind of platform, app hosting platform as a service platform. And it was basically written to say, if you want your app to work on our platform and you want it to work well, here are the kind of the design guidelines that we stick to. And it covered 12 different areas. I think it was made about 10 years ago, nearly by now. Some of these 12 factors, they've evolved a little bit. Some people nowadays talk about 15-factor apps and all sorts, but I'm focusing on these core 12 factors, just kind of explaining what they are, what they might mean for your development teams, and how kind of these changes are realized in practice, and what the kind of the benefits of those are. So kind of starting at number one, the first kind of factor says that there should be one code base that's tracked in revision control and has many deployments. Now, source code control isn't new to hopefully anyone here. But having said that, I was at a customer a couple of weeks ago, a small development team of 5, but they were still storing all of their code on NFS shares without any kind of source control or revision history. So those kind of practices are still out there. The idea kind of between this factor is that there is a single code base for an individual service. Now, when I talk about app, I don't actually mean the whole Uber solution. That's actually a solution. When I say app for the next kind of 12 factors, I want about that individual payment service or that individual web front end. And you'll see why kind of as we work through. So yeah, the individual code base for our payment service should live in source control, be that Git, Subversion, CBS, whatever. As long as it has some kind of source control, you're along the right way, on the right track. Small code bases are better in kind of almost every regard because they're easier to maintain, they're easier for developers to get on board with. They also tend to be more efficient in a number of ways. If a code base has got quite massive for an individual service, then it's highly probable that that service can probably be split again. It should be one code base for each function. As I said there, the payment service, just deals with payments, nothing else. It may be over time that payment service could be divided down even further. In some places I've worked before, a payment service is about 4 or 5 individual services, one that deals with each payment network that's out there, or with each payment processor that the customer kind of has to deal with. Got bolded there, dependency management. So this is, talking about code dependencies here. Almost all libraries and frameworks have some dependency management capabilities, but there's still a lot of people out there that aren't using them. Using them makes their lives, significantly easier. When we say up the top, one code base, many deploys, as kind of the graphic on the right indicates, this is kind of where containers can come into play here, because we have our single code base that makes us a single container image. We can then deploy that container image hundreds of times. It's the same image that's being run, same kind of responses are being given to queries to it. That means that our deployments are reproducible. It makes maintaining different environments, prod and dev, a lot easier as well. So the second factor is all kind of about dependency management. Explicitly declare and isolate dependencies, it says. What this is talking about here, and it's in bold at the top, never assume an app dependency is present on a host system. So if we take a look at Java programming, a common library that a developer might need might be log4j, now a common logging library. In the past, and this is really kind of especially true of things like Java and Ruby, they would ask the operations team to install the log4j package on the host operating system. Rather than do that, the recommended approach is actually to use whatever programming language's dependency manager or package manager. So, npm if they're dealing with a Node.js app, and to then ship those dependencies bundled into the application. And there's a very good kind of reason for this. As a developer, on my developer laptop, if I'm using, say, Ubuntu, which is very common, I will be using Ubuntu's version of log4j if I make a dependency on it. Whereas the production team will be deploying on top of SUSE. And we'll have, even though it may be the same version number of log4j, we'll have our own fixes and everything backported. The application might work slightly differently between a vended and a non-vended version of a package. By including that library or dependency with the code, usually in the form of a container, it avoids that problem altogether. Log4j on the host operating system is never going to be touched. This also avoids the problem of missing dependencies as well. Okay, configuration. Storing configuration in the environment and not inside the code. Now, when I used to work as a build engineer and release manager, the number of times I'd come across hard-coded passwords or hard-coded anything into the code that's put people around here laughing. Almost everyone here is smiling in some way. It happens all too often. And the third factor is all about that. So anything that isn't actually code and is part of the environment shouldn't be inside the code. It's as simple as that. This is one of the higher kind of priority factors out of all of the 12 factors. It's very important. Not doing this, aside from just kind of being bad practice, causes all sorts of headaches when it comes to deploying the code to different environments. By putting them as environment variables, I can deploy a dev environment super easily. I just put in the dev database details as an environment variable and pass it in. And the same with production as well. And containers and tools like Kubernetes provide really easy ways to manage environment variables and whole ecosystems around this as well. So there's really kind of no excuse for that not to be done. And doing it will bring a lot of benefits further down the line. One of which, kind of tying into that nicely, is backing services, and treat backing services as attached resources. So a backing service is anything that the app may consume, usually over the network. What we're talking about here is databases, message queues, technologies like that. Quite often, what would happen is a developer may bundle a database technology with their application. This is referring to splitting that out, no longer coupling it, making it loosely coupled, and then via an environment variable, receiving database credentials and an address to then go off and connect to. But it is important that if that database isn't there, that the application doesn't just error out completely and crash. It has to keep retrying, soft failure, keep retrying to connect. And this is really important in microservices because our services, different ones may disappear at any time. Cloud native, a cloud VM may be shut down at any time by the cloud hoster. So by running multiple instances of your individual service and having loose coupling to the services that they depend on, mean that they will just simply keep retrying until whatever they depend on is back up again. Number 5, this kind of deals with how we should build, release, and run applications. And it basically says that any service should have a separate build cycle, a separate release or run cycle as well. And this kind of boils down to building code is simply compiling it, turning our raw code into an executable. Actually releasing that code is taking that binary and pairing it with a set of environment variables or environment-specific configuration, and then deploying that code and running it. It's quite rare that I see people still tying together building code and running code in the same step, but it does sometimes still happen. If code is built and deployed in the same step, it probably means that they're ignoring factor 3, where it deals with setting environment variables for backing services. It means that we can let developers manage the build phase. They know how their application compiles. They're best place to manage it. A lot of the tools and frameworks out there as well, make this super easy. They really differentiate between building code and releasing code. And that's kind of another note that we don't touch on here. Using frameworks like Spring when dealing with microservices makes developers' lives a lot easier, because they've already got all of these kind of factors and technologies and ideas in place. So where available, they should be encouraged and used. So number 6, processes. This really deals with the concept of state. So it says that our services should be a collection of stateless processes. Persistent data should be stored outside of the application, for example, in a database or message queue. What that results in, as it says there, is that the state of the whole system is defined by what's in the database or the shared storage, rather than individual running instances. It means that the VMs or the containers can crash and die, and the service can easily be brought back up by connecting a new instance of that container to that same shared storage or that same database. And Stephen's going to talk about how some of the cloud provider technologies out there make this step super easy as well, by saying that developers should no longer even worry about databases, and they should use the databases out there on the public cloud, for example. But I'll let him talk about that. And what this does is, when this is applied, it helps our overall solution become cloud native. Now, it may be fair to say that not everything can be stateless. Sometimes there has to be data persisted somewhere. In the example of the taxi application earlier, we've got user data and ride data. Now, each individual service that generated that data, that may or may not persist data. It really shouldn't persist that data itself. What it should do is use messaging to send that data on to other individual messages, tools like RabbitMQ, for example. And then there will be a series of workers at the end that will take that data and commit it to the final data store. Now, the dealing with state is a complex topic, and we could spend a whole day talking about it in its own right. But in general, driving towards stateless applications will help make your services, significantly less vulnerable. Port binding. So, exporting services via a port binding. Now, the application should be completely self-contained. This is what this is saying. In the past, we may have, for example, with Java applications, relied on a Tomcat application server to actually host and make that application available to the outside world or to other services. And what this is basically saying is, don't do that. Almost all language frameworks these days provide technologies like Tornado and stuff to be able to run a local HTTP server that's available just for that specific application to use. Don't get me wrong, you're still going to need something like Nginx somewhere in the environment, but that's usually going to be at the front end, or it's going to be at the edge layer before entering into your services. When dealing with microservices, almost the individual services that are run, they're all running on random ports. They're not all running on port 80, for example. Each individual service will have a port that it binds to, and it will bind to it as localhost. One of the main reasons that we do this is because it allows other applications to become the backing dependencies of other parts or other services really easily. It means that the payment service, by binding to a port and exposing a stable API, can be consumed by any other service within our entire overall solution. And that's really powerful because you've no idea what, further down the line, what service you're going to want to create. So by saying all services should be available over HTTP or have a stable API of some kind, makes this a lot easier. It also means you're not dependent on, like I say, Tomcat or other application servers, WebLogic and other horrible things like that to deal with that, because that web server is actually made by the application itself using, like I say, the Tornado library or something like that. It's run entirely in user space. So, number 8, concurrency. Scaling out via the process model. And this is ultimately, it's saying that your service, each process within your service, the process should be normally these days, we would actually say normally just one process. When the steps factors were created, it was still quite common to have multiple processes for each individual service. But with the rise of containers, quite often there's just one process that's running it. And saying this is how you again can break down applications. It should be one function that should do one specific job, and it should be the best that it can be at doing that job. Nowadays, like as it says there, the factor is kind of a little bit less relevant. But one of the things that is relevant is we don't deal with daemonization anymore. An individual microservice shouldn't be dependent on systemd, for example. The container engine in Kubernetes takes care of all of that for us. When the service is launched, it's launched into the foreground for reasons I'll talk about when we deal with logging. But by following the concurrency model, it allows us to scale things really easily. And as I mentioned there at the bottom, actually, Kubernetes liveliness probes is the example of how we deal with this in Kubernetes, where what that says is you tell Kubernetes, my microservice, which is exposed on this port, when you go to this port, it should return a HTTP 200 OK code. And if it doesn't return that, then it's no longer alive. And then when Kubernetes detects that, it will go in and restart that container automatically. And this is where it's important for that container to also be stateless, because if it had state in it, that state was now just killed by Kubernetes. So you can kind of see how a lot of these tie into one another quite nicely. Number 9, disposability. And this ties in with what I was just saying. The process of each individual microservice absolutely must expect to be stopped and started at a moment's notice. Some people may have heard of Chaos Monkey by Netflix, which just goes in there and destroys random machines within their infrastructure to prove that all of their individual services abide by this kind of model. And it is really important, because when we do start dealing with microservices at scale and we implement containers in Kubernetes, Kubernetes will kill a container without warning at a moment's notice. It will send a standard SIG-term to the container to kill it gently, but that service has to be able to stop quickly. It has to be able to stop before it gets force killed, and it also has to be stopped gracefully. It has to try and make sure that it doesn't leave dirty data inside of our production database for something to then go and pick up. Our microservices have to be robust against sudden death, and they should also be ready to serve requests as quickly as possible. Now, kind of that part is a little bit less relevant these days, especially in the world of Kubernetes, because we can, like I mentioned earlier, we can have a readiness probe with Kubernetes that checks to see if an application is ready to serve traffic and won't send traffic to that specific container until it can. Now, environment parity, factor 10. It's all about keeping development, staging, and production as alike as possible. And it almost goes without saying, we've all been saying this for many, many years. But still, there often can be differences between them. A good example I mentioned earlier, using Ubuntu on a developer laptop, but deploying to production on SUSE. There's going to be all sorts of differences between those two environments. And this is where technologies like Kubernetes as well can come in. Because if our development environment is on top of Kubernetes and our microservices are running in containers on Kubernetes, and the same as production, it makes that super easy to make sure that those environments are alike. And even more so when dealing with cloud application platform, because it can often be that dev and prod are the same environment, just different, isolated parts of that same environment. Now, log management, treating logs as event streams. I mentioned earlier, if we package up our service, our payment service, into a container, the way that container is started, the service should be logged. It should start into the foreground. It shouldn't demonize. It shouldn't go to the background. And this is one of the reasons why we do that. In a kind of modern Kubernetes, environment, it's often expected that applications log to standard out. They just log to the console that they're running in. And this allows really easily for Kubernetes to collect these logs, or our platform that's running the application to collect the logs and ship them off. But also, if you've got 100 different microservices as part of your overall Uber solution, that means you've got potentially 100 different ways that they were writing log files if we were doing things how we used to do. 100 different ways that individual developer could have decided to route those log files. So by having the blanket rule of make logging an event stream and log to standard out, it makes that super easy. There's no more ambiguity between the different environments. It also means, because now we've got an environment variable, as mentioned during one of the earlier steps passed in, super easy to turn on debug logging for a specific service. This probably is still very much important, because logs are the primary way we can tell when something's going wrong with one of our application instances. We don't SSH to an individual container to diagnose it. We look at the overall pattern or trend. We observe the overall trend that the logs are telling us, and we look and we see, there's been a slightly higher number of 402 errors or whatever error coming out of the application today. Let's go and investigate. And that's when technologies like tracing and stuff come into play for us to allow to trace those kind of individual requests. It also means that we can ship all of the logs off to a central logging server really easily. We don't have to scrape logs. They can be shipped off and then archived for later, data mining purposes, for example. A good example of this is Elasticsearch, Fluentd, and Kibana Stack, as used and often in the Kubernetes environments. Often those tools expect us to log to standard out and make it easy to scrape. Now the final one, admin processes. Running admin or management tasks as one-off processes. Again, this is one where nowadays with tools like Kubernetes, it's slightly less important. But what it's saying is quite often we'll have an admin task that needs to be run, say upgrading the schema when dealing with a Ruby application, for example. It used to be the case that we would create a dedicated development environment for that task and test it and do all sorts before running it on production. What this is actually saying is run those admin tasks in the production environment, but just launch a set of instances that are pointing to a development version of the database first. But that development version of the database is actually for production database. It's just a snapshot of the production database that you took relatively recently and archived off. And again, by doing that in the production environment, it avoids problems where if the developer's done all of their testing on their dev machine, they may be using a version of Rake that's different to what we're actually finally going to use when we do it in production. Now in the world of Kubernetes, we have jobs for this purpose, and allow developers to write a specific job. But ultimately, one-off admin processes should be run in an identical environment as the regular long-running processes reside in. Those admin tasks should be run against a specific release that we took from our single code base that we had earlier on. So that's kind of my bit finished. Going through the 12 factors. I'm going to hand over to Stephen now. He's going to talk about how public cloud can help.
Thanks. So, good afternoon again. As I go through this, I'm probably going to try and ask you a couple of questions on the 12 factors just to see who was listening. All right. So you're all under a bit of pressure, okay? So we'll see how we go. So look, I wanted to talk a little bit about public cloud. Not for too long, because the party is in just 35 minutes in the tech showcase, and we all want to be there. So look, I think public cloud has been around for probably more than 10 years, all right? And I think the value of it is pretty well understood, but I just wanted to call out a couple of value points about public cloud because it lends itself quite well to the world of microservices. So the first one is talking about the limitless resources. Now, if you think about scaling an application, was scale mentioned in one of the factors? Question one.
Yes.
Which one? Is he right? Okay. We haven't got anything to give away, otherwise you get a prize. But okay, so the fact is, public cloud provides this amazing pool of resources, right? And it's described as limitless, but there is obviously a limit to it because it is a data center somewhere. But you have to work really hard to consume everything that AWS or Google or Microsoft have to offer. All right. So that's very difficult. That's pretty impressive when it comes to having to build this out on premise. If you're like a retailer or something like that who has particular peaks and troughs in their usage cycle and how they scale these applications, if you had to build that out on premise for your peak usage time, you'd be building out something like this when perhaps for 11 months of the year you're only using 10 or 20% of that. So the fact that you can use a public cloud, consume what you need to when times get busy, and then rein that back in during the quiet times and only paying for what you use, fits perfectly well to the concurrency piece. The next one is about experimenting, all right? And the fact you can do this with low cost and low risk. And again, if you've been around for long enough, you understand that perhaps when you took on a project in times gone by, in order to work on some new bit of technology or some new project or deliver a new application, maybe you had to buy resources into your company. Maybe you had to buy a new server and put it in the corner. Work on that project, see if it was a success or not. And if it wasn't, then you still have that server sat in the corner. You still made an investment which you're still paying for. Now, hopefully you can reuse it, but you never know. Again, with public cloud, you can experiment, you can design new applications, consume resources as you need, and then if it doesn't work out for your business, you just turn everything off and walk away. And all you've done is consume the time used so far by yourself, and of course the cost of the infrastructure, but there are no further costs that form a part of that project. So the risk is very low. It allows you to innovate just that little bit faster. Now the next one is speed. Now I think Rob realised how old I was the other day when I told him I used to get paid by a cheque. I used to have to, I used to take that cheque to the bank and pay it in, and 3 days later I'd get my salary that I could spend. Now, the world of IT was just as slow back then. I used to work for a dealer where we used to deliver services or applications to companies, and the way we do that is we'd phone up and order a bit of tin, a server or something like that, and then we'd wait whilst it was built. It would come in, put the OS on, put the app on, drive it to the customer site, rack it and stack it, and it gets delivered to the customer. And that was a process of weeks. Now, the fact that you can deliver now with the public cloud within seconds what used to take weeks makes speed completely irrelevant, right? So you can deliver stuff so quickly, there's no excuse for not being able to do things on time. And the last one I wanted to pick up of this slide actually was service orientation. So again, which factor was it which talks about consuming services as resources externally? Anybody? No? I'm sure it was 4. Was I listening? Maybe I wasn't listening. Anyway. Point is this, all right? Consuming services from public cloud organizations, it makes life simple. You're not necessarily coding all these things into your application because they are available to consume by people that have already written them. Now, some of these are potentially databases, but there are any number of other services that you can consume. I mean, one of the simple ones which I saw a demo of recently is Amazon Poly. So if you want to do text-to-speech, you could spend time focusing on writing that code yourself and trying to figure out how that works, or you can just use Amazon service and throw a bit of text in and get some real-life voice back to you. So whilst it's, you might be keen to start consuming services as quickly as possible, there are reasons why you might not want to do things on the public cloud in the new way. So let's take a database as an example, and it's probably the most relevant. So if you are an existing organization that has a database service on-premise already, then you've probably got the teams to look after it. You've probably got the DBAs to make sure that it's up and running, working well, highly available, and so on and so on. You've also probably got a set of existing processes on how to look after that, a series of runbooks on exactly what you need to do. And it might make sense to lift and shift that methodology out into the public cloud. And go into the public cloud, just spin up a server and get your DBAs to build out the database and do it that way. And that might work fine, but if your organization's big enough to have all those people and all those staff that are capable of doing that, that's fine. But maybe if your organization's smaller, you don't have that sort of resource available to you. So that's why you might consume database as a service. And there's a huge amount of databases you can deliver. So Microsoft has SQL as a service. If you go into Amazon, they've probably got about 10 or 20 different databases you can consume for different use cases. And that extends out into Oracle's cloud as well as Google's as well. So as well as being made available to smaller organizations, because they, like I say, they don't need the skills on site, the next thing is scalability. So again, if you've got an on-premise database or you've kind of created your own in the public cloud and you want to scale that out, then you need to pretty much manually do that yourself. Either if it's on-premise, you're talking about buying new bits of hardware, new memory, new disk or something like that. If you're consuming as a service, it's just a case of asking Amazon or Google for a bit more space. So whilst consuming services are a good thing, there may also be a reason why you might want to do things yourself. So one of the services you can consume is a Kubernetes environment. So Kubernetes is available as a platform on pretty much all the major hyperscalers out there. And you can get Kubernetes up and running very quickly and with little need to feed and water it. It's just a case of you then throw your applications at it and it tends to work quite happily. However, there might be reasons why you want to do that yourself. And as Rob's already mentioned a few times, containers do lend themselves very well to this microservices architecture that we've described. But if you want a little more control, then you need to think about deploying Kubernetes yourself. All right? And that might be down to the fact that you either need to replicate something from an on-premise world into the cloud with a specific Kubernetes version, or perhaps you want to experiment with a brand new version, which the CSPs don't yet support. It's all about having that little bit of extra control. So it's always a balance. Either sometimes choose a service, sometimes do it yourself. And with that, I'll hand back to Rob to finish.
Thank you, Stephen. So yeah, as I mentioned earlier, the 12 factors now are quite old in the grand scheme of things. They may seem quite esoteric, but they do have roots in good systems or good services design. People far smarter than myself have been debating this for years and have kind of come up with these common patterns, as being good ways to produce software. So we'd be kind of silly to kind of, not at least listen and see perhaps how we could apply some of this to our applications, and start thinking about how we can, breaking off parts of our application and doing some of these things. Because businesses that don't probably are experiencing problems that they don't know about. Usually, one of the biggest problems is actually just getting stuff released. Getting that entire solution built and deployed and launched can be a huge challenge. I worked at an optical retailer in the UK when I was a build engineer, and it would take us 2 weeks to do a release. And that's after a 6-month period of development. We worked in waterfall, and that was actually purely just actually getting the code built and turned into about 50 RPMs. It was a complete nightmare. It really slowed down the ability for fixes. When stores requested a change, it would take so long to get that change out to them. And by doing some of these, we can avoid a lot of those pains. So it's definitely worth a chat, with your development team about. And I'm sure they want to start moving towards some of these principles because it makes their lives easier. And then happier developers usually means better code, which also then usually means you've got a better product overall, and it can help give you the edge over your competition. So always worth kind of seeing if you can review the application design and take some of these points on board. So yeah, kind of that's it from me now. So I guess see if there's any questions from anyone. Oh, yep.
So you talked about the application parts. What about the API management? What kind of process does that become? Because take the taxi application, you will have many APIs, and how do you manage all that?
Okay, yeah. So the question just for the recording was, we've this is how we manage applications, but what about the APIs? The answer to that is it depends. As with a lot of these things, there are a lot of different API frameworks out there that can be used. I mentioned Spring earlier on, for example. Comes with its own set of frameworks for managing APIs, and it's going to be different for different languages as well. The important thing is that the APIs are documented and that documentation is published for other developers to consume elsewhere. It is absolutely worth looking into, API and API schema management tools. It all depends on the tooling that and the languages that your developers are using for what one is appropriate for them. But it is almost vital to have one, absolutely, because otherwise it can become we go from being a wild west of applications to the wild west of APIs, and that can be almost more detrimental to software development. APIs will have their own releases as well as the application itself, and that's another area that's important as well as having a defined deprecation policy for your API within your company. How far back do you want to go? By all means, that new payment service supports Google Pay, but if you drop version 1.2 when you release Google Pay or version 1.6 and you've got dependent services on that, then you're kind of, you get yourself in a right old mess. So deciding what works for your organization and documenting it and using some API management tooling goes a long way in making that pain easier. It's one of the the drawbacks of this. It's not all sunshine and roses. There is sometimes a little bit of extra work, but quite often the way that that a lot of these toolings work is that the API documentation is baked within the code itself. Devs don't have to do any more work in documenting the APIs that's done as part of their code. So, this is not too bad. Good question. Any others? Cool. So yeah, go enjoy dinner and or the party, sorry. Is there food? Yeah, and yeah, thank you for coming.